Okay. That's fine. To no avail. No problem at all. I got the homework, so I'll try to grade those as fast as I can. When do we need to have all the assignments done?
Yeah, I actually don't know.
I think she needed to say. Is the last day of that class?
Yes, I think. Yeah, I'm not sure.
Okay. Yeah. Awesome. Thanks.
Hey, William, can you hear me okay?
Yeah,
Okay, great. All right, going. All right, hello, good morning, everybody. I hope you're doing well. We have made it to the end of the term, yay. Couple quick announcements, so just as a reminder, you do have your 5.5 mini quiz due on Wednesday, as well as the chapter 5 quiz. And so you'll have to make sure that you set aside enough time to make sure that you can do that throughout the course of the day. Any homework that you are turning in late for partial credit to Wiley is due by Friday at 11 p.m. And then over the weekend, we will compute the homework grades and add them to Moodle so you can see what your final grade is at some point before Sunday to help you make a decision about whether or not you want to take the optional final, which is on Monday. If you do decide to take the optional final, there's no penalty for taking it. So if you do worse on the final than your other stuff, then nothing will change. But it is scheduled from 10:30 to 12:30 p.m. on Monday, and you will have to take it in a 1 hour block in that 2 hour period. So you'll have to start by 11:30 a.m. in order to have an opportunity to complete it. The optional final is cumulative. It is 10 questions that cover all 5 chapters, and it's the same structure as the chapter quizzes, so multiple choice, and it's all on Moodle. So I posted a link to the review that William did on chapter 5. So if you want to take a look at that, if you've been working on the chapter 5 review, that is posted on Moodle. And then drop-in help, we still have drop-in help today and tomorrow, but after that, the TAs have their own finals to study for, and since our last big assessment is on Wednesday, Wednesday is the last day for drop-in help as well. So if you need help on any of the old homeworks, make sure you stop in tonight or tomorrow night to get that help, okay? I think that's everything for announcements. So I am gonna switch over to the doc cam. 1 second here. Okay, and then I'm gonna just turn off my video for the bandwidth here. There we go. Okay, so the last section that we're gonna cover is what's called total change and the fundamental theorem of calculus. So obviously something called the fundamental theorem of calculus is pretty important. And so I wanna sort of tell you what it is, why it's important, how we're gonna use it, and how you might see it in the future. So there's actually a couple different parts to the fundamental theorem of calculus, and we are only looking at the first part, which is sort of the most common part of the fundamental theorem. And the fundamental theorem works as a bridge from Math 127 into Math 128, or for Calculus 1 into Calculus 2. And so I'm going to describe to you what it means, and then hopefully it makes sense, and then I'll talk about, what we're going to do with it. So the fundamental theorem of calculus says that if f prime of x is a continuous function on a and b, the interval a to b, then the area under the curve, which is what we've been finding, gives us the total change of the original function. And that is the same as if we had the values for the original function on these endpoints and looked at the difference. Okay, so let me give you a brief example. So we've talked a lot about velocity. So let's say we looked under a velocity curve and we found the area to be 100 and it represented 100 miles. So we knew that the original position changed by 100 miles, right? By doing some area under the curve. What this theorem says is if we had the position function and we knew the position at point A and point B, we could just look at the difference and that would also give us 100 miles, right? And so that, sort of like, yes, of course that's true. So why didn't we start with this, right? Well, the reason why we didn't do this, right, look just at the difference between the starting and ending point, is because in chapter 5, our premise was that we only have information about the derivative, right? The whole idea was we don't have the original function, so we're using the derivative to tell us about the original function. And so what this sort of bridge does is it says, okay, well, if we had the original function, this calculation would be a lot easier. And so the first thing that you do in calculus 2 is you start talking about how do we go from the derivative to the original function algebraically, right? So we learned all the techniques to do derivatives. So in calculus 2, you learn the techniques to undo that, which is called finding the antiderivative. So going in the other direction. So this sort of sets up that question. If we only have the derivative, how do we find the original function, right? So instead of just finding the area under the curve, we want the whole entire function, right? So we are not going to do that in this class. We are not going to be finding the original function. But if you do go on to take calculus 2, that's where you will sort of start with the work. That's where this picks up. So what does this mean for us? So we're now going to be thinking about, okay, we know how to find area under the curve. We approximated it, right, with tables. We did shapes on graphs to get area under the curve. We learned how to plug it into the calculator. But what we can do is we can use the fundamental theorem to help us answer questions about the original function that are a little more specific than what we've been doing. So again, we have figured out how much the original function changes by finding area under the curve. But if we have information about the original function at one point, we can get more specific information about the other point. Okay, so let's do an example together to see what this looks like. So example 1, suppose ice is forming on a pond at a rate of dy dt equals the square root of t over 2 inches per hour. If y represents the thickness of the ice in inches at time t in hours since the ice started forming, estimate the thickness of the ice after 5 hours. Okay, so we want to know the thickness of the ice at time equals 5. So a couple things I want to point out, okay? The original function is y. Y represents the thickness of the ice, and it's actually y of t, right? So the thickness of the ice at time t. What we want, right, in this sort of whole scenario is y of 5. What is the thickness of the ice after 5 hours? This is our goal. This is what we want, okay? What else do we know? We know the rate at which the thickness is changing, so y prime. And we also know, just from sort of thinking about what we know about ice and things like that, is that the ice starts forming at time equals 0. So right at time equals 0, there is no thickness to the ice, right? The original thickness is 0, and it grows from there. So how do we use the fundamental theorem to figure out the exact thickness at time equals 5? We've already kind of done this low key in other examples where we talked about initial values, but now we can do this formally. So if we were to integrate our rate from 0 to 5, our rate is the square root of t over 2 dt. That's going to tell us how much the thickness changes. And the fundamental theorem says this is the same thing as the original function at 5 minus the original function at 0. Now remember, we are really interested in the thickness at 5. So if we were to add this y of 0, whatever this value is, if we were to add that to the other side, we would have y of 5. So if we add this to the other side, what does that look like? right? So if we were to add that over, we would have y of 5 equals y of 0 plus the integral from 0 to 5 square root of t over 2 dt, right? So if we add y of 0 over in front, we get this equation where now we have the value we want. But in order to actually have that value, we need the numbers for y of 0 and the change, which is represented by this integral. Okay, well, y of 0, the initial amount of ice, is just 0, right? Because we're starting measuring right when it's starting forming. The integral, this is something we can plug into our calculator. This is what we had been practicing by plugging in different types of functions. So if we plug this into our calculator, we're going to get 3.726 inches. Okay, so 3.72 inches is how much the ice has changed. We add that to the initial thickness of 0, and we find that after 5 hours, the thickness of the ice will have to be 3.726 inches. Okay, so if y of 0 had been a different value, we would be adding that on. So let's say the initial thickness was 1 inch, right? Then we would have 1 plus the total change. If it had been 4 inches, it'd be 4 plus the total change. It happens to be 0 here, but it's oftentimes that this value is not 0. And because of that, we are able to solve specifically for a secondary value. So that's how we set it up. So we're going to try a couple of examples trying to sort of put this into practice. We're going to look at examples 2 and 3. So example 2, we have a cup of coffee that's 90 degrees Celsius, so it's very hot, and we bring it into a 20 degrees Celsius room. So the room is colder than the coffee when time equals 0. The coffee's temperature is changing at a rate of R of t equals -7 to the 0.9 to the t degrees Celsius per minute. So that's the rate at which the temperature is changing with time in minutes. We want to approximate the coffee's temperature when time equals 10. So we want to set this up using the fundamental theorem, and we want to ultimately know the temperature after 10 minutes. For example 3, we have a graph where the graph is going to show us the change in water in liters per day over the month of April. So this represents the 30 days from day 0 to day 30, from April 1st to April 30th. And we see that there's an initial amount of 12,000 liters of water. We want to set up an integral to represent the change in the water using the fundamental theorem and use that to approximate the amount of water on April 30th. Okay, so we're going to try these two different types, so the algebraic type and the graphing type. I'm going to give you about 4 to 5 minutes to try to do out these two problems. Make sure you set up what you think the problem will look like using the fundamental theorem, and then solve from there. And then, of course, we'll go through it together. Okay, take about 30 more seconds. All right, so let's start with example 2. So we have this cup of coffee and we want to set up an integral to represent our situation here, right? And so we know that the fundamental theorem says that we're going to integrate our rate. So the rate at which the temperature is changing is -7, 0.9 to the t dt. And we're measuring what's happening from time equals 0 to time equals 10. So this is what we want to find the change in temperature. And the fundamental theorem says that that's going to give us the original function value at 10 minus the original function value at 0. So we have to come up with something to represent the original function. One of the conventions that we have in math is that if you use a lowercase letter to represent the rate, we commonly use the uppercase letter to represent the original function. So I'm going to use r of 10 minus r of 0. If you used a different letter to represent this, that's totally fine. Okay, so what we're looking for here is the temperature at time equals 10, so after 10 minutes. So what I'm going to do is I'm going to add this r of 0 to the other side so that we have this r of 10 solved for. So r of 10 equals r of 0 plus the integral from 0 to 10 of -7, 0.9 to the t dt. Okay, so now the question is, which values do we know and which ones do we have to figure out? So r of 0 is the initial temperature. So capital R represents the temperature at any given time. And so there's two values in the setup of this, and we just have to figure out which one's the right one to use. So it says there's a cup of coffee that's 90 degrees Celsius and put into a 20 degrees Celsius room. So R of 0 and what we're measuring is the temperature of the coffee. So we want to use the 90 because we are measuring the coffee temperature and not the room temperature. And now we have the initial temperature of the coffee and then how much the temperature changes. So to find this value, we need to plug this into a calculator or computer to find the area under that curve. So when we plug all that into some sort of calculator or something like that, we get -43.27, and that's in degrees. So we see that we started at 90 degrees, and then we decreased by 43.27 degrees. So we add those two numbers together, as is, since this one's negative, and we find that after 10 minutes, the coffee is 46.73 degrees, and this is in degrees Celsius. Okay, so we're using the fundamental theorem and what we know about rates of change to talk about the value at a specific point. Okay, so let's look at the next example. which is similar, but now we're working with a graph. So here we have the rate of change in the quantity of water in a water tower. And we're measuring this in liters per day in the month of April. So we're going to start by just setting up the integral that we are going to be working with here, just so that we remember what we're looking for. So I'm going to do it on this piece of paper just for, actually, I'll do it over here for the sake of space. So we're integrating over the 30 days. We want to integrate the rate at which the water is changing. Now, we don't have an algebraic rate here like we did in the last problem. So since we don't have the rate, I'm just going to write f of t dt to represent the rate. So we'll talk about that in a minute. And we know that that represents the amount of water on day 30 minus the amount of water on day 0. Okay, so this is the original function. So this is the amount of water in the tower, and this is the rate at which the water is changing. Okay, so again, what I'm interested in here is the quantity of water after 30 days. So I'm interested in f of 30. So if I solve for that, f of 30 is going to equal f of 0 plus the integral from 0 to 30 f of t dt. So then the question is, do I have what I need to solve this problem? Well, f of 0 is the initial amount of water. And I know from the setup that I started with 12,000 liters. So I do know the initial amount, right? But I need to add to that the amount of water that changed over the 30-day period. So I can't put that into a calculator because I don't have the function. However, I do have a graph, and so I can use the area under the curve by approximating the area under the curve on the graph to get this total change. So a couple things I have to remember about the graph. Well, one is that any area below the x-axis, I'm going to count as negative, and anything above, I'm going to count as positive. So I'm going to split this into those two categories. So from day 0 to day 12, I can see that the area underneath is negative. This looks pretty triangular to me, so I'm just going to do this as a triangle. There's a couple different ways you can do this, and I'll show you the other method on top. But you may not get the same exact answer as me, but you should get something in the same ballpark. Okay, I'll talk about what that ballpark is in a minute. So here for this area, right, I'm looking at 1/2 base times height. My base is 12 units long. My height is -50, right? And so when I multiply all that together, I get an area here that's going to represent a change of -300. So however you did this, you should certainly get something between, say, -200 and -500, something in that area. If you got something like -45,000, then you're way, way off. So, you know, something in the negative couple hundreds here for that first piece. Now, the other way that we can approach this, which I'll do for this top part, is to instead try to approximate the number of boxes, right? So if something doesn't look like a shape like pretty easily, another approach you can take is find the area of one box. So here, this is a 6 by 50. So each box is 6 by 50. So each box represents 300 in terms of area. And then I can approximate the number of boxes that I see in my picture. So I have one full box here, 2, 3, 4, and then I'm going to pair this with this to make box number 5. And then similarly, I'm going to pair this area and this area to give me box number 6. If you are doing boxes, you really don't want to go any smaller than half a box, right? So you may have gotten like 5.5 boxes or 6 boxes or 6.5 boxes, but you don't want like 6.125, right? So either a whole box or half a box is what we're sort of working with. So here, that means my upper area, I'm saying it's approximately 6 boxes, and each box is 300. So that gives me an area up here of 1,800. So that's the 6 times 300. So now my total change, which is what I'm looking for here, is the addition of all these areas. So I have 1,800 above. So I increased by 1,800 liters, but I also decreased by 300 liters. So I add these together and my total change is 1,500 liters. Okay, and obviously if you approximate it slightly different, then your numbers are slightly different and that's fine. So I have 12,000 plus approximately 1,500. Add those together, I get 13,500 for my approximation. So no matter how you did your approximation, you should have something sort of plus or minus 1,000 from what I got. So something between 12,500 and 14,500 is where we should land for the total water in this particular tower. And no matter what, we should have something above 12,000 because we have more area that we added than we decreased. Okay, so let's look at another example with a graph, because graphs can also help us get values on original functions, more than just one value, but actually a whole bunch of values, which help us to start thinking about how we get to an original function. Okay, so consider that we have the graph of f prime of x here. In addition, we know that f of 0 equals 2. So notice this is f of 0, not f prime. So this is not a value of f prime of x. This is a value of the original function. Use this information with the graph above to fill in the following table for values of f of x. Okay, make sure you are careful and you justify how you got that. That just means show your work. Okay, so we'll do the first value together, and then hopefully you'll be able to see the other ones here. So the way that we want to set this up is that we know the value of the original function at 2, but we want to see what the value is when x equals 1, right? So when x equals 0, the function has a value of 2. When x equals 1, we want to find that value. So the fundamental theorem says that if we were to integrate from 0 to 1, right? So 0 is what we know, 1 is what we want, of the derivative, that would give us f of 1 minus f of 0, right? But f of 1 is what we want, so we're going to add that f of 0 over. So f of 1 equals f of 0 plus the integral from 0 to 1 f prime of x dx. So whatever the value is at f of 0, we start there and we add on how much we change from 0 to 1. Okay, so f of 0, that was given, that has a value of 2. And then from 0 to 1, we're looking at how much our function changes based on the graph. So again, area under the curve. From 0 to 1, we have a triangle here. Okay, so if we do 1/2 base times height, the base 0 to 1 is 1 unit, and the height is -1. So here we see we're going to change by -0.5. So -0.5 is that area, and it's negative because it's below, so it tells us we are decreasing. So 2 plus -0.5 is going to give me a value of 1.5. So now we need to do that same process to go from 1 to 2. So we'll set up an integral from 1 to 2. We'll then solve for f of 2. We'll get that value. Then we do the same thing to go to 3, 4, 5, and 6. The one thing I want to point out here is that when we change over at 4, everything over before 4 is negative, and everything after 4 is going to be positive. So just keep that in mind. So I want you to take about 3 minutes, see if you can figure out the rest of the values on this table, and then we'll go through it together. Okay, take about 30 more seconds. All right. So using sort of the map from the one we went through, if we want to find f of 2, we're going to be doing f of 1 plus the change from 1 to 2 of f prime of x dx. And so you can see that if we were to subtract this back over, we would have the same setup as the fundamental theorem. So f of 1, we have 1.5. And now the change from 1 to 2. So if we look at our picture and we look at what's going on between 1 and 2, you can see that we have a rectangle. And so the base is 1 and the height is -1. So we're going to have a change of -1. So to this 1.5, we're going to change by -1. So if we subtract 1 from 1.5, we get a value of 0.5 for f of 2. Now for f of 3, we'll come up over here. We're going to have the same map. F of 3 should equal f of 2 plus the change from 2 to 3, f prime of x dx. Well, f of 2 was 0.5. And then from 2 to 3, we again have a base of 1, a height of -1. So we're going to change by -1. So -0.5 plus -1 is going to give me -0.5 for the value of f of 3. For f of 4, we're going to have f of 3 plus the change, right? Just like we did before, from 3 to 4, prime of x dx. F of 3, that's the value we had, -0.5. The change from 3 to 4. So the change from 3 to 4, we see again is a triangle now. 1/2 base times height. The base is 1. The height is -1 times half is going to give me a -0.5 here. So -0.5 plus -0.5 is going to give me a -1. And then for f of 5, it's going to equal f of 4 plus the change from 4 to 5, f prime of x dx. So f of 4, which we just found, is -1. And then the change from 4 to 5, notice that this is where we switch to being positive, right? So now we're above the x-axis. So we see a triangle here. We have 1/2 base times height. The base is 1, the height is 1 times half, means we're adding a positive half here. So -1 plus positive half gives me -0.5. All right, and then last but not least, we're trying to find the value at 6. And so f of 6 equals f of 5 plus the change from 5 to 6, f prime of x dx. So f of 5, we just said was -0.5. And then we want to approximate how much we change. So we have this rectangle here, right? So we have a base of 1, a height of 1. So we're changing by +1. So -0.5 plus 1 is going to give us +0.5. Okay, so now we have all the values we wanted on the table, but I just want to give you a quick reminder of what this represents. Okay, so the original picture we have is of the derivative, the rate of change, and we are using that rate of change to find values on the original function. So even though we don't know how to take an algebraic function and turn it back into something, we can find values on the original function. And we could plot these points if we wanted to get a sense of what that original function might look like in terms of its shape. Now, we already have some information based on what we learned back in chapter 2 and 4, which is consistent here, but now we're able to get values, and that's what's really important. And one of the key things that we needed to get those values is a starting value. If we didn't have this information that f of 0 equals 2, we could not get any of these values. Instead, we only know how much the function changes based on the derivative. So if we have a starting value, we can then add the changes to that value. But if we don't, then we can only talk about how much the function changes, but we don't know where it actually is in space. So in order to get values on the original function, you do need to have an initial data point, okay? So let's look at another graph where we're going to do a little bit of what we were doing here, but we're also going to do some tying back to some things we learned about first and second derivatives back in chapter 4. Oops. Okay. So here's what we're looking at in example 5. So in example 5, we have the velocity of a moving object is given in the graph below. So for the sake of doing this particular problem, let's assume, all right, that's 5 and this is -5. But let's assume that, anything positive is going to move forward and anything negative will move backward, because you're going to have to talk about this a little bit. Okay. So what we want to do with this information is we want to describe the motion of the object over the first 10 seconds. So when is it moving forward? When is it moving backward, right? How do we know? So think about that. Part B. So B and C are talking about acceleration and deceleration. So this is a graph of the velocity, and acceleration is the derivative of velocity. So this is something we haven't really done since chapter 4 and chapter 2. So we have to think back on what the first derivative tells us about the second derivative and see if we can put that together. And then part D, we are looking for how far this object is from its home base at different times. So this is where we're going to be using area under the curve to talk about how much the position has changed. Okay, so there's 4 different questions here. And then again, just as a reminder, like I just said, usually, well, where can I write this? S of t is position. That's the original function. That's not what we have here. Here we have the derivative. And when you take the derivative of position, you get velocity. That's the graph we have here, right? So velocity. And then again, if you take the second derivative of position, which is the first derivative of velocity, that's when you get acceleration, right? And which is what we're talking about in parts B and C. So this is really talking about the second derivative of position or the first derivative of velocity. Okay, so this one's a little tricky. You really need to think about how these things interact, but I'm going to give you about 4 minutes to see if you can work through these 4 problems. Again, part D is looking specifically at area under the curve. Part A, you could use the area and calculate it, or you can just look at when it's positive and negative and talk about it. And then B and C is really when we need to think about the relationship between the first derivative and the second derivative in this context. Okay, so take about 4 minutes and then we'll go through it together. Okay, take about 30 seconds. All right, so let's go through these. So let's start with part A, where we're going to describe the motion of the object over the first 10 seconds. So if we look at where time equals 10 is, we're considering what's happening from 0 until 10. And so as I mentioned, if we have something positive, we're going forward. And if we have something negative, we're going backward. So if we look at where this changes, right, we see that t equals 4, that we change from moving in a forward direction to moving in a backward direction. So that's one way we can talk about this, right? So t equals 0 to t equals 4, we're going forward. And if we wanted to know exactly how far forward we were going, we want to calculate the area under the curve. So here we see that we have a 4 sort of base and a 4 height, and this is a triangle. So 1/2 base times height is going to give us 8, and this is going to be in meters. I don't think you guys can see the units. So the velocity is in meters per second, and time is in seconds. So it's going to go forward 8 meters, okay? Because that is the amount of area, which tells us the change in position. But then at time equals 4, something changes, and we see that from time equals 4 to time equals 10, we are going backwards. How far do we go backwards? Well, we need to calculate the area under the curve again. So I'm going to break this up into a triangle and a rectangle. So this triangle goes from 4 to 8 and then goes down to -4. So from 4 to 8 has a base of 4 times -4 times half. It's going to give me -8 for this area. And then from 8 to 10, I have a rectangle with a base of 2 from 8 to 10 and a height of 4. So that's going to give me 2 times 4, which is another -8. So when we go backwards, right, we're going backwards by -8 plus -8, which is going to give me -16 meters. Whoops. Apparently I'm writing on 2 pages here. I'll try to line that back up. So backwards by -16 meters. So that's a good way to describe the motion. You could just talk about forward and backward, but actually finding how much it changes is going to be important overall. And we will use that in part D anyway. Okay. So for part B, it says, what is the acceleration of the object during the first 8 seconds? So let's look at where 8 is. So 8 is here. So time equals 8. So the first 8 seconds is this line that goes from time equals 0 to time equals 8. How do we think about acceleration from a graph of velocity? Well, we remember that acceleration is the derivative of velocity. So we want to approximate the derivative of this function. And what we notice is that this is a line. We know that the derivative of a linear function is the slope of the line, right? So that goes back to when we were learning about this in chapter 2. So if we can find the slope of this line, we know the acceleration from time equals 0 to time equals 8. And so I will point out that since this is negatively sloped, that this is actually going to be decelerating during that time. I think acceleration is going to be negative because the slope of that line is negative. So how do we get the slope of a line? Well, in order to get the slope of a line, we're going to pick 2 points on that line and do the change in y over change in x. So I'm going to pick the point 0, 4, which is where it crosses through the axis there. And then I'm going to pick a second point on the line. I'm going to pick where it crosses through here since I've already labeled it, which is 4, 0. But you can pick any other point on the line. So we have the point 0, 4 and the point 4, 0 to get the slope. I'm going to come down here and do slope. We're going to do the change in y over change in x. So the change in y, we have 4 minus 0. The change in x, we end up with 0 minus 4. Now I get a slope of -1. So during the first 8 seconds, the acceleration is -1. And we also say that we decelerate by 1 if our acceleration is negative. So we are slowing down, okay? For part C, we're going to explore this idea a little bit more. And we're going to say, during which times are we accelerating? Which times are we decelerating? And when are we constant? So we know from our work in part B that when the slope is negative, we're going to be decelerating. And if you look at this picture, the only time we have the negative slope is during that first 8 seconds. So we'll start with that. So we're going to be decelerating from time equals 0 to time equals 8. Okay, we're going to be accelerating when the slope is positive, right? Which means that we are going up from left to right. So if I look at where that's happening, let's see. That is time equals 12 until 16 is the first time I see it going up. So time equals 12 to time equals 16. But I also see it going up from 20 to 24. So here. So also time equals 20 to time equals 24. And then when is that acceleration constant? So that's going to be when our slope is 0. So that's going to be when we're sort of flat here. And we see that that happens from time 8 to time 12. And then again from 16 to 20. 16 to 20. And then again from 24 to 30. Okay, so again, for parts B and C, this is really hooking back to things we learned a while ago and trying to tie them into what we're learning now. And then for part D, suppose that at time equals 0, the object that's at home base, how far away from home is the object at time equals 4? So at time equals 4, we can see that we have changed by 8 meters. We already found that in an earlier sort of calculation. And at time equals 12, right? That means we have most of our calculations done, but we actually have to add in a little bit more, right? So let's see, let's do that in black. So from time 10 to time 12, that's another 2 by 4. So that's also going to be a -8. So if we're trying to figure out how far away we are from the base at time equals 12, we need to add up all the areas from 0 to 12. So we have 8 plus -8, which is 0, plus -8 is -8, plus -8 is -16. So we are -16 meters away from home. Now, what does that mean to be negative meters away from home? Well, remember, these types of problems are talking about position. So for the first 4 seconds, we went 8 meters, forward, and then we turned around and we went backward. So we went 8 meters, and then another 8 meters, and then another 8 meters. And so this is 16 meters from home, but since we go backwards from home, that's what the negative represents, -16 meters in this direction, so backwards. Okay, so this one was a little tricky, but hopefully you were reminded of some of the things we talked about earlier, and you can see some of the differences in the way we word the different questions to talk about different things that we're interested in. Okay, so the next example we're going to look at is this sort of common example of the fundamental theorem of calculus as it comes up in business. Okay. So when we talk about business, this often comes up in terms of cost because we have this idea of fixed cost, which is in itself an initial value. And so we've been using these initial values in some way to talk about all sorts of things with the fundamental theorem. And we can also do this when we talk about cost functions. So if we were going to apply a cost function to the fundamental theorem, just sort of in its sort of regular form, we would write it like this. So if we were to integrate marginal cost from A to B, that would give us the cost of B minus the cost of A, right? So it's the same fundamental theorem we had before, but instead of F, we're using C because we're talking about cost. Now, typically, right, what we're going to be sort of looking at is that our A is going to equal 0. Okay, so we're almost always looking at situations where we want to know the total cost to produce 45 items, which means 0 to 45, or 150 items, so 0 to 150. Our starting point is almost always 0. And I want to remind you that C of 0, if A is 0, is our fixed cost. Okay, so if we take that into consideration, and we rearrange our equation like we had been doing with the other ones, we would get that the cost to produce B items, whatever that may be, is going to be the fixed cost plus the change in cost from 0 to B, C prime of Q, dQ, right? So this idea of fixed cost ties in sort of directly with the fundamental theorem, which is why this is the common way that we look at this. So if we want to know the total cost to produce some number, this is sort of the setup we're going to use. So we're going to look at an example that has a lot of different parts to it. So here we have the graph of marginal cost of some item, okay, and it's given in this graph here. I tried to sort of highlight where the boxes were. This is the 2, 4, 6, 8, 10, 12, 14, 16, and then across here, 50, 100, 150, so on and so forth. This is the quantity. So for part A, we want to set up an integral to represent the total cost to produce 150 items of this product. So we just want to set it up using the numbers we have here, using C prime of Q, just to have a general sense of how the integral looks like. For part B, we're going to estimate the total cost to produce 150 items. So again, we're going to use the area under the curve. And if you are not given a fixed cost, you can assume it's 0 unless you are told otherwise. So in part B, we're assuming that fixed costs are 0. For part C, it says, suppose now that there's an additional fixed cost of $1,000 to produce this item. So part C is the same as part B, only now we have a fixed cost of 1,000, and we're asking, how does that change our solution? Part D, so now we're going to sell this item for $25. We want to write a revenue function. So we have to remember how we generalize revenue. So price times quantity, how do we set that up? And then how do we find the total revenue for 150 items? And then part E, find the total profit earned by making and selling 150 of these items. So for part E, we're going to be using our results from part C and D to compute our profit for part E. Okay, so I'm going to give you about 5 minutes to work through these. There's quite a few pieces here, and then we will go through it together. Okay, take about 30 more seconds. All right. So for part A, we just want to set up the integral to represent what we are trying to look at here. And so here, when we use the fundamental theorem and we set up our integral, we're interested in 150 items. So that's 0 to 150, c prime of q dq equals c of 150 minus c of 0. We can write it that way, or alternatively, we can write this as c of 150 equals c of 0 plus the integral from 0 to 150 c prime of q dq. So these represent the same thing. This second one is just solved for c of 150, which is what we want. And this is just sort of the original formation of the fundamental theorem. Both of them are fine and represent what we're looking for. For part B, we want to use the graph to estimate the total cost to produce 150 items. So this is where we're looking at area under the curve to try to figure out what, the area is going to be, which is going to represent, what we're looking for in terms of total cost. So again, you can approach this by counting blocks. You can try to put in shapes. And again, your estimate may not be exactly the same as mine, but it should be in the same ballpark / relatively close. And I want to point out that we are looking until 150. So we're not doing this entire graph. We're just going out till 150. So the way I did this is I broke it up into two pieces where I had a rectangle, and I noticed that there's a little extra area, which I'm going to take care of in the second part. But I did a rectangle, which had a height of 6 and a width of 150. So 6 times 150 is 900. And then I wanted to fit in a triangle, okay, to represent what was going on here. And so my triangle, I fit in to look like this. And what you'll notice is it's not quite enough area, right? There's some extra, it's an overestimate, but I'm going to keep that in mind in terms of like my general answer here, right? So here I only went up to 100, 1/2 base times height. So my base is 100, and then my height goes from 6 to 15. So my height has 9 units to it. So 1/2 100 times 16. Nope, not 16. Just kidding. 9. Sorry about that. From 6 to 15 is 9 units. So 1/2 times 100 times 9, that gives me an approximation of 450. So that's one way you can do it. Again, you could count blocks. You should still end up with something in the ballpark, but I did it this way. If I add those up, I'm going to get 1350 as my approximation of the total cost. Okay, and so your approximation should be somewhere in the 1200 to 1500 range, so depending on how you did it. So here again in part B, because it didn't talk about fixed costs, we are assuming that the fixed costs are going to be 0. For part C, we have the same area under the curve, but now we're assuming a fixed cost of 1,000. So remember from our integral in part A that we want the area under the curve plus the fixed cost. So for part C, we're going to take the area we'd gotten before and add in this new fixed cost of 1,000. So this becomes $2,350 for our approximation. Obviously, if you have a different answer than me for part B, then you'll have a different answer than me for part C because you're just adding 1,000. For part D, now we're talking about revenue. So we are making the assumption that we can sell whatever this item is for $25. First, we want to write an equation to represent the revenue function. So as a reminder, revenue is price times quantity. And here we're saying that we're going to sell them for $25. So in this instance, our revenue function will be 25 times Q. We want to find the total revenue for selling 150 items. So my revenue for 150 items will be 25, which is the price, times 150, which is the number of items that I'm going to sell. And that gives me a revenue of $3,750. Okay, so that's the amount of money I take in from selling my item. So finally, in part E, we want to find the total profit earned by making and selling 150 of these items. So for part E, I want to remind you that profit is revenue minus cost. And so we have the revenue at 150 items, which was 3,750, minus we have the cost, which was 2,350. And again, if your cost is different than my cost, then your final answer will be slightly different. But when we subtract them, we find that we have a profit of $1,400. Okay, so there's a lot of pieces to this particular problem, but hopefully you remembered from the stuff that we've been working on throughout the course how to answer each of these different pieces. Okay, so let's look at another example of how this might come up. Okay, so we'll look at example 7. The total cost in dollars to produce Q units of a product is C of Q. Fixed cost is $20,000, and the marginal cost is given by C prime of Q equals 0.005 Q squared minus Q plus 56. Part A, estimate C of 150, so the total cost to produce 150 units. Part B is to find C prime of 150, so what is the marginal cost at 150? And then part C is to use parts A and B to estimate the total cost for 151 units. So I'm only going to give you about 2 minutes to try this out because I want to make sure we have enough time to go through it real quick. But I want to remind you for part C, you're going to be thinking local linear approximation. So take about 2 minutes, see what you can sketch out, see what you can figure out, and then we will quickly go through it together. Okay, take about 30 more seconds. Okay, so we're going to quickly go through 7, but I do want to mention example 8 is the last example in the lecture videos, and you do have to use a left and right hand estimate. So if you want to try that at home, you can try out that example and then check out the solution on the linked lecture. So for part A, the cost to produce 150 items is going to be the fixed cost plus the change in cost from 0 to 150. We know our fixed cost was $20,000. That was given in the problem. And to find the change in cost, total cost, we have to integrate this. So we do have the function. So this is something we would do on a calculator or a computer. And when you plug it in, you get 2,775. So that is the additional cost on top of the fixed cost. So when we add those together, we get 22,775 is our cost to produce 150 items. Part B asks us to find the marginal cost. So we're taking 150 and we're plugging it into the marginal cost equation that's given there. When we plug that in, we get 20.01. And what that tells us is that it's going to cost us an additional $20.01 for each additional item that we make when we are making 150 items. Okay, so that's the marginal cost. And then for part C, we want to use parts A and B to approximate the total cost to produce 151 items. So this is local linear approximation. It's been a while since we've done that. But for local linear approximation, you have to have the value of a function, the derivative at that same point, and you want to know how far away you want to approximate. So we need the cost of 150 items, which is what we found in part A. So 22,775 plus the rate at which the cost is changing. So $20.01 times how far away we're predicting. So 151, 150, that's 1 unit away. So we add those together and we get that our total new approximation for 151 is going to be $22,795.01 is our approximation for the cost of 151 items. Okay, so again, the last example is on Moodle on the lecture page if you want to see how that's done out. Otherwise, you should be able to do the homework and the 5.5 quiz with the stuff we did today. So good luck on those and stop by Drop In Help tonight or tomorrow night if you have last minute questions.